try and go find what those were. I don't. I'll ask Mike to be sure, but I don't think he's expecting you to change or adjust what problems you're working on based on these changes. That's
Yeah,
just
I mean,
my gut feeling that it's not a very helpful thing to do for you.
yeah, and that's fine. And it would be beneficial anyways for me to do it, because I think all we've done, the previous one was just deriving, so the penalty method, and we never even touched the niches method, and so it would obviously be beneficial for me to do that. But I'm just kind of curious if it was how much it built upon.
I'll ask
derivations.
him.
Okay.
I'm pretty sure all of the coding you're supposed to do is still using the penalty method, and so that shouldn't affect the rest of your work. But we'll get with Mike and ask him what he thinks on that.
All right, sounds good to me.
If it helps, I've got the questions handwritten.
No, we have history, so I can go through and grab all the questions. That's not the issue. I'll just make sure. I mostly want to talk with Mike and see what he's intending here, because I think what he is thinking is, oh, I need to break this up and change things. So he's looking to the future of this class and thinking about how he wants to do it. But we'll see how that affects you guys in the present. So.
And to be clear, any of you can view the history on the wiki there, just with the right there. Yeah. This is view history.
You'd have to dig through it a little bit, but it's all there. So if there's something that was explained a certain way before that you're trying to find, you can go find that.
That's good to know. At the end of this class, or through the next couple of weeks, will we have partially working FEA, flex method program? So we should be working towards putting one together.
Yes, absolutely.
Okay.
That is the. I mean, I know that was an exercise from before, but that has not changed. I guarantee he still wants you to be working through your code for the whole method.
Okay, because that will help.
Together.
That will help direct efforts, and that will be really nice.
Yeah.
Chris or Kyle, do you guys know, so and we just went over on the page of the penalty method where they talk about the statement of the elastic energy, I believe it was. Do you know where I can find that, like where that is derived? Like before we get into like the strong and weak form, like where those two equations, 2 and 3, are actually derived from?
Where these potentials come from?
Yeah. Like, would that be in like my mechanics book from like 203 that I took from Dr. Scott?
Different pieces of it will come from different places. You can probably find the internal energy portion that probably will be in your 203 book.
That's this guy right here.
Or something along those lines will be in there.
Okay.
And then the other two terms on that line, that's really just balance of linear momentum.
Mm-hmm.
And so like that's all that those are. The panel or the Lagrange multiplier stuff, you'll find that in a lot of different places, but it won't be in your 203 stuff. So one place that this material is taught is in mechanical engineering 575. Is that the number? The optimization.
Optimization.
Yeah, the optimization class. You can find it there. There's a little bit of that in. Oh, they don't teach that class anymore. over in the math department, I imagine that there's probably something that goes over so really what that second what 3 is, those are optimization techniques there. And so you can find, so any good class on optimization will probably cover similar techniques. And this is just taking those and applying them to a mechanical system.
So it's optimizing using, in this case, a Lagrange multiplier.
So it's more of how do you enforce a constraint on a system? So if you're trying to optimize something and you have the constraint that, like, let's say you're optimizing some sort of geometry, and you have the constraint that a point on the geometry can't change at all. Like that might be an attachment point
Right.
for the geometry that you're creating. You would use methods like this to do stuff like that, to kind of like put a constraint on your optimization.
Okay.
So constrained optimization is where you'd find a lot of this.
Yeah, it allows you to build in constraints into your objective function so that you can actually solve for, it allows you to include things in your objective, where in this case, our objective is minimizing the energy of the system. So that's one way to think about how we're doing this here, is that this is the potential energy of a system,
Right.
and this is the constraints on that system, and we're building those into sort of our optimization, where we're trying to minimize the system. That's a good question, though. I personally am still learning a lot about these potentials and how they're used. So,
Well, because I'm curious, like in the future, if we have to derive like our own equations, whatnot, like maybe the elastic energy. I mean, so I'm curious, in like what class would we? I guess Kyle already answered my question. What classes would we take to like talk about that, so we can, in the future, maybe, if we had to come up with our own method or equations to start from, that we had to derive the weak and strong and everything from. So,
Yeah. So the internal energy portion, that's probably the portion that is most important to understand if you're going to be deriving these methods later on. And that field is more what's known as continuum mechanics.
Okay.
yeah. And Kaylin, to answer your question, I know that Mike has planned to go into continuum mechanics in this course. So if you stick around with us, he will start to talk more in depth about what these potentials are and
Right.
how we use those.
I know from my standpoint, I don't know if any of the other students felt this way, but like when he pulled these, like I probably seen 2 before, at least the first part of 2 before, but like when he pulled 3, it almost seemed like he was pulling them out of a hat. I was like, I didn't really know where they came from. And for me, it's generally like it's sometimes helpful to see like where equations are derived from to like understand what they're doing, other than people just tell me what they're doing. And so I was kind of stuck on that for a little bit, but thank you for your.
They were
help.
pulled out of a hat, just not Dr. Scott's hat.
We could probably give you a pretty good explanation of where the second term in equation 3 comes from. But the first term, we'd have to get into some mathematics a little bit to, to really understand where it comes from. You can look at the weak form, like what happens to the weak form with those equations. Like you end up with the actual equation that you need to satisfy your constraint. So that's really where the Lagrange multipliers come from. It's more of like, we're going to enforce this constraint on the system in the weak form. What would the potential have to be for that to come out? So that's really where it comes from.
Okay, thank you.
We play games. That's okay. That's what Kyle was saying. That's a good question, though. Other questions?
This is more of a generic class question. So you talked about how this class is going to extend into next semester and then beyond. If we can't fit the next class into our schedules, are we still going to have access to this wiki beyond this semester?
I think so. I think Mike would be fine with that. You'd have to ask him, but I don't see any reason that he would shut off access to this.
I think
You'll have to ask him.
interesting.
That's a good question, but
Yeah, it's be interesting to continue to learn it. I just don't know if I'd be able to fit the class itself. So
right.
Just like following the sun.
Okay.
Other questions?
So I see that he's been posting a lot of like some pseudocode, and it has some kind of like MATLAB kind of annotation to it for the algorithm that we're going to be putting together.
Mm-hmm.
Is there any algorithm out there that is complete that we could, especially for those of us in industry who may not have enough time to really dedicate to fully developing this on our own, but that we can play around with? Does that exist?
Almost. So I've actually been tasked with putting together a more a complete version of all of this that I think he's intending to make available to students of the class, both from industry and otherwise, where it does a little bit more than what he's going into here, even where it'll allow you to pull in more complex bases, it'll allow you to plot things, etc. That's being developed in Julia, so it's not MATLAB, but it is Julia, which is a close cousin and better in my opinion. But we won't get into that. But that is coming, I think. I don't know when he wants to turn around and make that available to you, but I do have working examples for all of this at this point, and I think he will make those available to you at some point. That being said, for the students who are taking this class, I think for now, I still think he wants you to really go through and do this yourself, and really start to understand what we're doing in each of these steps. So does that answer your question?
Yes, thank you.
Okay. That's a good thought though. I mean, that we've had the exact same thought where, especially with the velocity that we want this class to take, I think we want to provide better resources for people to go in and do some of this on their own. So
Chris, could you, I think we talked about this a little bit, but could you speak a little bit more to the invert geometric map function just before assemble K?
Sure. So this has changed since the conversation. We talked about the inverse map on Monday, right? So he's changed this so that it's now a pre-processing step. For the purposes of this code, it doesn't really save us a whole lot of time to compute this map at the beginning. But when we start looking at dynamics and you're going to run a problem multiple times, essentially you're going to assemble K, you're going to assemble F and assemble B on multiple time steps. You're going to dynamically change the system over time. One of the really nice things about the methods that we're developing is that this inverse map can actually come out at the beginning of all of that. So you can compute it once, and once you have your parametric location that you need to evaluate, that never changes. Even as your geometry deforms over time, the parametric location doesn't change. So that's one of the really neat things. So that this is kind of highlighting that fact that we can pull the inverse map out of all of this assembly, and we can pre-compute kind of the element and the XC. So again, this has changed a little bit. This is some of the feedback that I and other people gave him. Originally, his inverse map was just computing an XC location. But what you really need is you need an element-specific XC location, right? Each element is defined parametric. So each set of Bernstein polynomials is defined parametrically from 0 to 1. And so you need to know from 0 to 1 where to evaluate that. So this now gives you an element and an XC location for both of the places that you need to invert. So where you're applying your constraints and where you are applying your force at L. So that's
why
that's sorry, what were you saying?
I was just asking if that's why it's only at the endpoints.
Mm-hmm. Yeah, you don't necessarily have to do it only at the endpoints. You could make this more general if you want. You could say like, so this constraints right here, he just assumes that you only have a single constraint. So B ends up being a row rather than a full matrix. But if you wanted to add additional constraints throughout your system, you could do that. And you would just pass in some vector of constraints, and it would actually go in and it would invert each one. So this is actually a mistake. So this invert map needs to come out because we did this inversion right here. So I will fix that. Caleb, can you make a note or just go in and fix it? Somebody, you can just make a note.
Fix it. I'll just take it out right now.
Yeah, just go fix that because this now can come out. Does that make sense? I don't remember who was asking that question, but you can have multiple constraints. The constraint that we're applying for this problem, we're kind of assuming that this problem is we're fixing it on the left and we're pulling it with some force on the right. But that's just a specific problem. You could generalize your code to say, well, what if I want to apply a force anywhere along the bar? There's nothing special about the ends of the bar. I can apply constraints anywhere, and I can apply forces anywhere. And that has, I'll get a different problem when I do that. So what he's doing here is he's saying we're going to apply a force at L and a constraint at 0. But more generally, you could say I can have any number of constraints or any number of forces across this length of the bar. And I can do all of this in the same way. All of this is applicable to those cases. The only difference is that you're going to have a little bit of extra computation in F and B, depending on where you're applying constraints and where you're adding forces.
Thank you.
Is that clear?
Yes, it is.
Okay, great. So feel free if you want to make your code more general so that you can apply forces wherever you want and do more interesting things. Absolutely, feel free to do that. But it's not a requirement. Other questions?
I may have missed this because I stepped on a little late, but is Friday a recitation again, or are we moving that to today?
I have no clue. Did Mike say? I know he updated the calendar invite. Did he say what he
My
was
my
doing?
my impression was that he was just switching today and Friday.
Yeah, that's what I thought too.
Okay.
Yeah, my guess is he'll want to jump in and keep pushing things forward on Friday.
So I have a question about your weak form equation, and kind of when you start to do other other problem sets. We have this uniaxial bar with a single point load on the end, but
Mhm.
do you have to generate a weak form for every problem type that exists out there, or is that something that eventually becomes more generalized? Is there a more generalized way of deriving that? Is it only for each type of physics that you have that you need a weak form, or is it for every like different, if depending on the geometry that you're using? How does that work?
Yes. So when you talk about every kind of problem, are you talking about like every kind of like force loading system, every
Like
kind of constraint?
I'm not really
That
restricting it to that. I mean, so you could have, so this right here, you have a 1D bar, right? You could have a 1D
Mhm.
bar with a body load on it, and he showed us kind of where you could apply the body load on this
Mhm.
as well.
Yeah, so that's actually so that's the body load
Right there, there's the body load. So you can have point loads on the system, and you can put as many of them you want, and you can do body loads on the system. But if you then also incorporate like thermal expansion, and now there is a temperature gradient on that bar or whatnot, so that's going to come from a different energy.
Yep.
Yes.
That's
So
exactly right.
yeah, so it turns into you have to start building a multi-physics solver. A lot of times when you do stuff like that, so you're going to have to essentially get the potential or the weak form that has to do with the thermal properties of the temperature of the material and how the temperature will move through the body, and then those equations get coupled together to like affect how the material would deform, because as your temperature goes up, it gets softer and stuff like that you can do.
So you never really have a weak form that's auto-generated. You have to manually generate a weak form for every type of problem case that you're going to allow your solver to do. That way you can feed that into your solver. But the solver will be able to solve these equations regardless of what the weak form is at the end of the day. But it's the weak form you have to generate for each solution type.
Correct.
Yeah. And this is something that he touched on a little bit last time, but you also have to think about I might say you don't necessarily have to derive. I mean, Kyle, this section may be something that you can answer. As I'm thinking about it, I think of the weak form and the consistent tangent as very similar ideas, where you have to derive the actual formulation for your matrix. Like you have to actually pull all of those derivatives through. We've talked about, though, the fact that you can use automatic differentiation. So if you had a starting point, if you understood the potential of your physics, if you understood or the residual, then you could back out from there the weak form or the consistent tangent. Is how maybe do you know what I'm talking about, Kyle?
Well, your residual is really your weak form, but I do know what you're talking about with the um, consistent tangent. I suppose if you give it if you gave it a potential, you could use automatic differentiation to figure out what your residual is, without having to bother with all of that. But problem with automatic differentiation is a lot of times it doesn't really lead to the most efficient code. And so if speed is what you're after, it's oftentimes better to go and figure out what it is yourself.
Right, just derive it. Anyways, I don't know if that answers your question, Eric, but
Yes, yeah, it does.
There-
Yeah,
the-
it's 'cause-
yeah, there are cases where you can generalize things a little bit, but you always have to tell it what are the physics of my system, right? Like it cannot just come up with physics automatically. You always have to describe the physics that you're trying to simulate in some way. And if your problem requires you to differentiate those physics for some reason, then sometimes you can do that automatically, or not sometimes, but in general, I think you could do that automatically. But you have to have some starting form for understanding the physics that you're trying to represent.
So my follow-on question is, in this equation right here, let's just take a bar that we've got this bar example, right?
Mhm.
So if you're applying a body force, there's a spot for that, and if you're applying a point load, there's a spot for that.
Mhm.
We directly, I can't remember exactly how we directly put in the boundary condition for the left that it wasn't able to move displacement wise.
That's the U naught right
That was the
here.
U naught. Okay, right.
Yeah.
So that went into that
Mhm.
one. So in terms of this, if you're going to put in other things, do you always try to like somehow relate a boundary condition to one of these three? So like, for example, if you have other things, sometimes you have, instead of having a body force, maybe you actually tied a certain region in a certain region of the part to ground, or a certain region of that part has a what am I trying to say? I guess contact would be something different than this, right?
Right. Are you talking about like contact, pressure, different
Yeah. So like if
kinds
I'm
of traction forces?
yeah,
Right?
exactly.
Because
So like
this is a traction force, but there are other kinds than just like a point load, right?
right. So like if you're doing like a traction force on a well, when you're talking about 1D, you don't have a lot of different options really.
Mhm. But you could do contact, and you could do, well, you can't really do pressure.
Yeah, so like pressure,
but-
would you need a completely different energy equation for the pressure? Is that a different physics that you're trying to solve for?
So pressure is just a different form of traction.
Yeah.
All that pressure is a traction that is normal to your surface. That's all that it is.
Yeah, so like for example, but I know in a 1D system, it's really it makes no difference. But there's a difference between a point load and a follower load, right?
Mm-hmm.
And so is that something where you could continue to use these equations and you would define the follower load in terms of something within the system, or would that be an extra part of your weak form?
So it doesn't. It really doesn't affect your weak form at all. It's really more when you get to your consistent tangent that things start to change. Really, the general concept is that you are applying some sort of traction to the boundary of your object. Now, that traction might depend on the deformation, might depend on how that geometry displaced, and you get a follower load, or it might be might be forced to be normal to that surface, and in that case you get a pressure. But at the end of the day, all of those are just tractions on the boundary. So they are all just the same thing. Now, how you treat it when you are trying to solve the system with the consistent tangent, that changes because as the body displaces, your normal is going to change, and so you have to account for those changes. Does that make sense?
Yeah, it does.
Yeah, one way to think about it in 1D, if we're just looking at this equation, Eric, this HL, right? This is the force that you're applying. HL could be a constant, or HL could be a function of U. But either way, HL is just HL. It's just a traction force that we're applying on a boundary. It might be a function of the displacement, meaning that it's a function of, right? That would be a follower force, right? If HL was a function of U, then HL can change as the body deforms.
Yeah,
But
right.
we're gonna formulate it in essentially the same way. Like it's not, yeah, like there is, I don't know, maybe your question is, what happens if HL is a function of U, and then you are right. If you differentiate this potential with respect to U and HL is also a function of U, there are other terms that pop out. That is true. Like this weak form, and correct me if I'm wrong, Kyle, but this weak form would not allow you to do a follower force. You would have to assume that HL was a function of U in order to get a follower force. That's my understanding.
Yeah, so the potential, starting off with things as in potential form, doesn't work as well for follower loads. It's better to start off with a strong form in that case. So really what happens is follower loads and stuff like that, they lead to non-symmetric matrices, non-symmetric stiffness matrices and stuff like that, which implies that you don't come from a follower load. Sorry, which implies that you don't come from a potential. At least a a C2 potential. It doesn't imply that. So, and so in that case, it generally just implies that you don't have a potential, so, to start from.
So if you don't have a potential, that does make it so that it is a different weak form equation that you're trying to solve. So do you have to derive a different weak form for each of those potential solution cases?
So it's more of that you start with the strong form. That's the more general, that's the more general way of getting the weak form, is starting with the strong form. You say, I want to satisfy these equations in the continuous case. What do the corresponding integral equations look like? So that's the more general way of doing things. And a lot of times your strong form, like in structural mechanics, it's really just conservation of linear momentum. That's really all that you start with. Did that answer your question?
A little bit. I understand the general gist of what you're saying. I'm still curious as to how it plays out when you're actually trying to write some of these algorithms, but you want your algorithm to be valid for, all the different use cases that are out there. Just kind of how do they go about, like if they're generating a program, you need a weak form in order to be able to solve the problem using finite element methods. So just kind of how do, like most softwares that are out there, get to their weak form for each case or scenario, how are they generating that weak form? So I understand kind of the gist of what you're saying. You don't always start from the energy method. Sometimes you start from a different point. And so I think it makes sense to me that if the more you expand your code to handle more scenarios, then the more programming of the strong form or energy equations or something. And that's why there's so many different methods, that you apply when you're doing FEA, because you're trying to leverage different equations. So I'm just trying to see where that's at behind the scenes. That's what I'm understanding. That's what I'm hearing from you.
Yeah.
Okay, great. I think that's all we have time for. Thanks, everybody. If you have other questions, feel free to post them on the forum. But otherwise, good luck on your codes. We'll make sure to tell the students what your assignments actually are. We'll make sure that that's cleaned up so that that's clear to everyone. So
Thanks.
Thank you. Talk to you later.
Thank you.